All right, let's go ahead and start. And actually, so what I'm about to, so I just told you kind of the, well, we went over in the last lecture why we want to look for gravitational waves. And then we went over some of the kind of cold atom atomic interferometry technology that we're going to use. And then what I'm about to tell you now is how to put it together, how to put those things I was just teaching you about together to make a gravitational wave detector, and then what we can see with that. But before I do, any questions on anything we were just talking about, something that occurred to you over the break or anything? Remember, you can either raise your hand or type in the chat that you have a question or whatever. Okay, great. So as always, stop me anytime you do. I'll go on. And now I'm going back to my keynote for this part of the talk. Okay, hopefully everyone sees my slides. If not, let me know. All right, so good. All right, good. So how are we going to look for gravitational waves? Well, to begin with, sort of the very basics, what is a gravitational wave? Well, somewhere, 400 megaparsecs away, two black holes or something, two very heavy masses are inspiraling. They crash together, and that acceleration of mass sends out this ripple in the metric, right, in space-time. If you've studied GR, you've seen this. If you haven't, you've probably still at least heard about the basic effect that after propagating 400 megaparsecs all the way across the universe to us in the lab, if we have two masses, for example, two mirrors of LIGO or atoms, and they're just floating around, then as the gravity wave, as this ripple comes through, the distance between these two masses, let's say it was originally L, okay, it'll now pick up some small fractional strain, some small fractional change of size h. H is a dimensionless number, the fraction of the length change, and it will oscillate with the frequency omega of the gravitational wave. Okay, so and remember those h's you saw on the on one of the early slides I was showing you. In fact, let's see if I can go back to them. Yes. We could be looking for things like 10 to the minus 18, 10 to the minus 20. Extremely small h's, right? This is this strain here on the y-axis. So you're talking about very tiny length changes between these masses, right? And that's of course why you want something absurdly precise like LIGO, right? If you have a kilometer long, 10 to the minus 18 of a kilometer is about a femtometer. So it's about the size of a nucleus, for example. And even smaller if you're looking for smaller strains. Okay, so that's what the gravitational wave does. It causes these tiny little length changes, or notice since it's oscillating in time, you could equally well call it accelerations of these masses, right? So I'm going to look for that. I'm going to look for that with these tools, the clock and accelerometer that I was just telling you about. Oh yeah, sorry, and I labeled the strain and the frequency of the gravitational wave. I think I'll try to hopefully stick with those variable names for the rest of the talk. So how should we go looking for a gravitational wave? Well, the kind of basic idea of almost any of these gravitational wave detectors, practically any of them, is I want two good inertial masses, these kind of gray blobs here, and ideally they would be free floating with nothing but gravity acting on them. And then I want some way to span the baseline between them, because I need to see this length change, right? General relativity, is only going to let you make these local measurements. So I need something that kind of goes across the baseline between them, maybe a laser. And then one way to talk about how to make these measurements is with then say, oh, I have a very good clock. So imagine there's a laser racing across the baseline. If I just have an excellent clock and I time how long it took to get across the baseline, right? Then if I very precisely measure, I'll very precisely measure the light travel time, since c is 1, this is the light travel time right here. And if I measure it precisely enough with a good enough clock, then I can see that it wiggles, right? I measure it, I take one shot, I measure it, I take the next shot, I measure it, it's a little smaller, I measure it again, it's a little smaller, and it traces out a cosine or something, okay? Or whatever the waveform, the actual waveform of the gravitational wave is. Okay, so that's the basic, that's the basic cartoon I want you to have in your head for a gravitational wave detector. Is that clear? Questions on that? Gotta get the chat out here. Okay. Okay, now I would say that LIGO more or less works this way, okay? Its inertial test masses are its mirrors, and they work super hard to vibration isolate them, etc. So they're free floating. And then you send a laser between them. Here's this laser interferometer set up for LIGO. so the inertial test masses are provided by the mirrors, the baseline is provided by the laser. LIGO doesn't have a good clock in the normal sense that you'd think about a clock, but I'd argue that actually the second arm of LIGO is really like its clock. In other words, you could absolutely see the effect of a gravitational wave even in a single arm of LIGO. The arm stretches and squeezes, and you'll see that. If you can precisely enough measure the distance across it, you could interfere the laser beam with the incoming laser beam, for example, and the effect of a gravitational wave would definitely be in there. But it would be completely buried under the noise of the laser. We do not make lasers good enough yet, anyway, to do it in a single arm. So the second arm is really the clock. It's really the thing that's stabilizing, if you like, the laser frequency, removing the frequency noise of the laser. Okay. By comparing the laser that's gone out and back on the one arm and the laser that's gone out and back on the second arm, effectively, or really comparing the length changes on the two arms, those have the same sensitivity to some wiggle in the frequency in the spacing of the laser. The laser itself is not a perfect clock, and so as the maxima shift, as the phase fronts shift, it would look like a signal of a gravitational wave. It would look like a single length was shifting, but of course, since it's the same laser, both arms will shift the same way, and you'll pull that out. You'll subtract that out. Whereas the gravitational wave caused stretching along one arm, while it causes, let's say, squeezing or nothing along the other arm, depending on which direction the gravitational wave is moving. Okay. So that's the basic idea. That's my sort of analogy that I want you to have in mind for LIGO. Is that clear? Are there questions on that? Okay, so how are we going to do with atoms? So here's our picture. Okay, here's the idea, which is I want to set up two atoms on either end of a long laser baseline. I want to do this because I need as much distance as possible to make a gravitational wave. Remember, you saw that the signal is HL. It's proportional to your baseline. So if your experiment has no baseline, if everything is right on top of itself, you can never possibly measure a gravitational wave. Okay. Some people propose things that violate that theorem, actually. But that was wrong. They're wrong. So you want as much distance as possible to amplify your signal as much as possible. So we're actually going to run two atom interferometers, each separated on the ends of a long laser baseline, because the laser can easily propagate kilometers, which is much harder for the atoms to do. We'll use the atoms essentially as our inertial test masses, okay? But notice I'm also going to use the atoms as a good clock, all right? And this is the key difference with LIGO that I want you to keep in mind. We would use just a single baseline detector here, because the atoms themselves are excellent clock. Each end of this baseline, I'm running an atom interferometer, and you can think of it for now like an atomic clock, which means on each end, the atom's wave function is being split, right, into this linear superposition we were just talking about, and then recombined, and I read out the final phase shift, run the interferometer on each end, and read out those two phase shifts and subtract them, okay? And I claim when you subtract them, when you take that differential measurement, you remove all this laser noise. Essentially, you're using the atom as a clock, okay? I'm not using the laser as a clock, so the atoms are very precisely timing how long it took the laser to get across the baseline. Another way to say it is as the laser passes the first atomic clock, it like starts it. It gets all the way across the baseline. It'll start this one, and then you'll see we'll send another laser pulse to stop both, and that'll measure the light travel time. I'll show that on just the next slide. But I just want to point out this crucial idea of using the atoms sort of as double duty. They're both the inertial test masses and the good clock. And there's a good reason for that, which I'll come to on the next slide. But is this basic point clear? Are there questions on this? Okay. There actually is a different proposal, a different way to do this, roughly. I mean, I'm glossing over a lot of details, but roughly there's a second way you can use atoms to detect gravitational waves, which is a clock proposal by these people here, very nice paper, which uses it only as the clock, and then you use a regular macroscopic proof mass as your inertial test mass. That turns out not to be beneficial on the ground, but it could also work in a satellite experiment. So that's something else worth keeping in mind. I'm just, for the sake of pedagogical simplicity, I'm just going to talk about this one way. It's also the way that most people who are building these things now are using. Okay. All right, so if no questions, I'll go on. So how do we propose to use this to detect gravitational waves? Exactly, this basic idea I was telling you. And this is something we call MAGES. Actually, there's now many detectors. I'm going to show you that in a second. But since I'm involved with MAGIS, and that's sort of where we started, let me just describe it in terms of that, although like I said, there's actually a lot of great groups working on this now. We're actually going to run it as a sort of hybrid clock accelerometer. So you remember I showed you those two sequences back a few minutes ago. I showed you the clock sequence, the pi/2, pi/2, and then I showed you the accelerometer sequence, pi/2, pi/2. And I said they were sensitive to different things. The clock sequence measures time. The accelerometer sequence measures acceleration. Used either one on their own, they each have some issues. And actually, there were many years when we were working on this when we thought you couldn't get around those. You had to choose one or the other, and you'd be stuck with those various noise sources. I don't want to go into too many details, although if you're curious, I can tell you more. But basically, the nice thing is then, after many years of thinking about this, we finally found a hybrid version. It's here. I'm not going to go into too many details, but you should think of it as sort of both a clock and accelerometer. Or in other words, it's using the atom as an excellent clock. It's using, we'll use what's called a clock atom, something that has these two metastable excited states. For example, like strontium was one of the very popular atoms to use for atomic clocks. We'll use some clock atom, and we'll make use of the beautiful properties of these of the very long-lived excited state of strontium. It lives much longer than a second, so it's an excellent clock for our purposes. We'll be waiting with interrogation times t that are a second or longer, so we need that. But we'll arrange it in a sort of accelerometer sequence. What you see here, the red and the blue, are when it's in the ground state versus the excited state. And if you go through this, I won't go through it now. You can try it on your own. It is a little complicated. What you'll notice is essentially what this is doing is measuring the light travel time across the baseline. I send one pulse, these are the laser pulses here, across the baseline, and then another pulse back. The first pulse starts the two atomic clocks, this one on this side and this other one on the other side. The second pulse stops them. The difference in the phase shifts, the difference in the time measured by the two atomic clocks, that tells you how long it took to get across the baseline. Actually, it tells you twice the light travel time across the baseline, right? Then we do something like this LMT that I was telling you. So actually what I'm showing on this slide isn't even the full complication. We actually do many, many, many pulses. And we measure that time many, many times, essentially because the more times you can measure it, the more precisely you measure it. In that way, we read in the light travel time across the baseline, but then we do this funny mirror pulse sequence in the middle, sort of like you saw with the accelerometer, and then we do a final funny beam splitter pulse sequence at the end. The end result of this is to essentially take a double time derivative of the time measurement of the distance across the baseline, and that gives us how much the baseline is accelerating, but as measured by these clocks. If you like, I'm doing a very careful clock comparison and looking only to see how much is one clock accelerating with respect to another clock. Okay, that was a little bit complicated. Let me pause there and ask, are there any questions? I didn't go through all the details for you, so I probably left you a little bit confused, but let me know if there's any questions right now. Okay. All right. Then how does the whole detector work? So you'd have some laser sources, these things I've labeled on the ends here, and then you'd be running you have some atomic clouds close to them, and then you'd have a long laser baseline between them. You want as much distance as you can get. On the Earth, think kilometers. In space, maybe even much, much farther. And these common laser pulses, you can see sort of back and forth from these lasers on the two ends of the space-time diagram here, would be running these atom interferometers. The atoms are measuring the light travel time across the baseline, as I mentioned, but the fact that it's also an accelerometer means I can use the atoms as an inertial proof mass. It actually doesn't care at all about the acceleration of the laser. That has been subtracted out by subtracting the phase shift in the two atoms, right? If one of these lasers jitters a little bit, which it always will because of that seismic noise, remember, like LIGO had that problem with seismic noise on the ground, that's what cut them off at low frequencies, right? Think back to my second slide or something. If this laser jitters a little bit, the phase fronts will be messed up, but each atom interferometer will read that in. They'll read that noise in the same way, and you'll subtract it out of the differential measurement. Okay, that's absolutely crucial. In other words, I'm just comparing the acceleration of one atom with respect to the other atom. Really, one cloud of atoms up here with respect to the other cloud of atoms down here. Okay, that's what makes this such a pristine measurement. The atoms are actually excellent inertial proof masses. Okay, first of all, they're not attached to the ground. We just drop them. You could do that with LIGO's mirrors too, and very briefly you'd win over seismic noise, right? But then the mirror hits the ground, and the mirrors are very expensive. You don't want to keep making new ones, so that doesn't work. But with the atoms are very cheap. We can always grab some new ones. So we just put them in free fall. And that's what I said. Remember, I said we're actually going to use the atoms not held like in a regular atomic clock. We're going to use them free. This is why. Because we want to completely remove that seismic noise wall that LIGO has at low frequencies, allowing our detector to go to much lower frequencies. So that's one critical point. That's one way you get around all the sort of proof mass noise that would otherwise stop you from going to lower frequencies. Let me pause. That's such an important point. Let me pause and ask, are there any questions on that? Is that clear?
Maybe you have something in the chat. So why don't you go ahead and unmute yourself?
Thank you.
So I'm just wondering, like, what happens when the seismic noise at S1 and S2 are different? What does that mean for the interferometer?
Yeah, that's a great question. And since we're imagining them being, let's say, even on the Earth kilometers apart, or if these were satellites, these would be two different satellites, as I'll show you in just a second. We would certainly expect there's no way we're going to be able to like rigidly attach them or otherwise tie their seismic noise together exactly. Yeah. So we'd be very worried about that exactly. And in fact, this is one of these deep issues that I only briefly alluded to when I said there was a long time where we actually thought that was inevitable. We had no way to get around that. Okay. Many of the early pulse sequence schemes that we had tried out for gravitational wave detection, they all fell prey to that exact noise. And then you just had to do some amount of seismic isolation. You won something, but it wasn't great. But then we came up with this scheme, which actually completely isolates you from that. And equivalently, by the way, laser noise. So if the laser jitters a little bit, if the ground that the laser is on shakes a little bit, that messes up the perfect spacing of the laser phase fronts as they come out of the laser. That's actually the same as the laser itself not being perfect. It's just not being a perfect metronome that puts out the phase fronts at exactly regular intervals. So every laser has some noise, and also the ground is always shaking. So for one way or another, these things will have noise, either seismic noise or laser noise or both, really. And they won't be the same, exactly as you said. That's actually one of the details of the sequence that I didn't really have time to prove to you. So I haven't really answered that question, but the way it works, let me kind of give you a crude idea. The way it works is one pulse goes all the way across the baseline. This pulse finishes, and only then after that does the next pulse start. In fact, they look like they're tied together here. They don't even have to be. I can wait as long as I want. That actually doesn't read into the differential measurement very nicely, which means this one pulse comes from only one laser. It reads as the starting gun of both atomic clocks, but any jitter in it will read the same way. It'll jitter both clocks the same amount, right? If the laser hopped back by a tiny bit of distance, and that made the laser pulse a little bit delayed in getting to the two atomic clocks, it'll be delayed the same amount in both. And then, of course, later, the second laser pulse comes across, but now it's just one pulse again. Yeah, it's got different seismic noise, but it's the same seismic noise in both interferometers, and it subtracts out. The crucial thing where noise can creep in, where something that's not common mode between the two interferometers enters, is if anything happens in the middle between these two atoms. Okay. So, for example, if something grabbed the laser pulse in the middle and jittered it, then I'd be in deep trouble because it would act on one atom and not the other. But that means all I'm really relying on is that the speed of light is constant, right? Is that when the speed of light, when the laser propagates from one atom to the other atom through some vacuum, it's constant. Now, the speed of light is mostly constant, but it does jitter a little bit because it's never a perfect vacuum. We do have some residual gas remaining. We pump those things down to 10 to the minus 9 torr or less. But there's some amount of residual gas, and it's even a tiny amount, but it has a tiny little index of refraction. And then there will be actually wind in that, in the vacuum, in the tunnel. And that's something we have to worry about, but we do. But you can calculate how much there will be based on thermal gradients and things like that. And you can find, we show that it's plenty small enough. So actually, basically, the speed of light between the two atoms is constant enough. Does that answer your question? Basically, that any jitter in the laser with this particular pulse sequence we've got is going to read common mode into the atoms the same way. Is that clear?
Yeah, that's perfect. Thank you.
Yeah, great. That's a really important question. In fact, like I said, we actually spent years thinking about that. So I don't want to, answering in a couple minutes is really too quick. I thought for years that didn't work, and I was very excited when I realized this pulse sequence. Yeah, that's a great question. Any other questions? Yes, I see a hand.
Yes, so my question has to do then, suppose that the group velocity of electromagnetic waves in some theory is time dependent. So could these experiments put constraints on these types of theories?
Absolutely. That's a great question. The answer is absolutely yes. In fact, if I get to it, probably not in this lecture, but maybe in the next lecture, I was going to mention some ways that dark matter can actually do things like that. I wasn't actually precisely going to mention time dependence of the speed, although that's possible too. But that's a great question. Absolutely, you're right. And in particular, let me just note, this is something that's a little bit special to this kind of single baseline gravitational wave detector based on clocks, based on atomic clocks that I've been pointing out. Notice that with LIGO, actually, if I go back to it, with LIGO, if I just vary the speed of the light, that'll mostly, to leading order, cancel out of these arms. In other words, it'll be the same signal in both arms. Of course, if I did it sort of non-uniformly in space or something, it'd be different. But if somehow in time the speed of light was changing a little bit, LIGO would not see a signal, right? But the atoms could potentially. I mean, depending on the exact details of your theory. Because I'm comparing to a very precise clock, the atoms could see that. So absolutely, great question. And in fact, that's part of what leads to our dark matter sensitivity of this too. So jumping ahead of myself here, since you asked, a gravitational wave detector is actually very similar to an ultralight dark matter detector, which is weird. I'm gonna explain that when I get to talking about dark matter. But actually, the two topics that my lectures are on are not as dissimilar as you might have thought in the beginning. The gravitational wave detector is an absurdly precise measure of things like space and time. Actually, that can look for dark matter too, which is pretty cool. In fact, very similar to ultralight dark matter detectors. Yeah, so great question. Did that answer it? Or any more questions?
Sure. Thank you very much.
Yeah. Yeah, great questions. Any other questions? Oh, I see another question in chat. Yoni, can you unmute?
Yeah. So let's see, Henry, can you unmute yourself?
Yeah. Hi, I'm just curious that if we were to implement this kind of experimentally, so you say that it's important for it to be under the influence of only gravity. Would it be like, because typically cold atoms have to be trapped. So would it be like kind of turning off the trapping potential just as in some ion-based quantum computation as well?
Yeah, absolutely. Great question. That's absolutely right. So I didn't really go through any of the details. You can kind of tell I'm a theorist here, and I'm trying to cover a bunch of topics, but you're absolutely right. So actually the way we have to make these, we have to, and I was going to mention a little bit later, a little bit about this. You have to make these atoms ultra cold. Remember, I said I really want to control their motion around, right? I don't want them just to have some random thermal velocities that are zipping off out of my detector and things like that. That's no good. I have to make them incredibly cold, and I do that exactly as he says by trapping the atoms in a trap and then applying all sorts of cooling techniques to them that are the subject of several Nobel Prizes. I won't go into. So absolutely, they start in a trap, and then that's right. Either in the current realizations, you could turn off the trapping potential. Or actually often a lot of the trapping potential is based on laser pulses anyway, or part of it is based on laser pulses anyway. So you actually just change the laser frequencies and stuff that you're using to release the atoms and instead make a beam splitter. Or actually another option is something that we're actually considering probably most likely for MAGES now is that you cool and trap them in one area and then you can shuttle them across. You actually shuttle them with the same sort of techniques I was talking about here. You can kick them with laser pulses, have them move this way and then stop them. So absolutely, that's right. So you first cool and trap them, you make a cloud, and then the way this experiment would work, then you launch that cloud or you run it through this whole sequence here. And actually, while you're doing that, you're also working on the next cloud of atoms. You're constantly shooting through shots, constantly shooting through bunches of clouds of atoms. And you should think this is about 1 million or so atoms at a time. Very cold and dilute enough that they're not interacting. They're actually acting like those independent atoms I was talking about in the atomic clock earlier. Yeah, great question. Did that answer the question?
Oh, yeah, absolutely. Thank you so much.
Perfect. Yeah, great. Any other questions? Oh, yes. One question, is this the same setup as for the Aeon detector? Absolutely, that's right, actually. In fact, I was going to show you. Yep, the next slide. Perfect question. So that brings me to my next slide. So actually, if you don't mind, let me just walk through it now. The answer is yes. And so actually, I was talking about that in terms of this MAGES concept that we had started with many years ago. But by now, actually, I'm really excited to see there's a lot of work going on. So let me actually go through that. You can take this basic concept I talked about, and people are now actually starting to turn it into real terrestrial detectors, which is really exciting for me, by the way. This is something I started as a grad student with some of my collaborators. We had this crazy idea to look for gravitational waves with atom interferometry. And it's been sadly many years now since I was a grad student. I'm not as young as I once was, but it is now finally coming to fruition. There's actual real hardware, and I can show you pictures, which is really fun. So the MAGIS 100 detector, we call it MAGIS 100. It's under construction now at Fermilab in a shaft leading to the neutrino beam, to one of the neutrino beams. It's about 100-meter. Oh, I'm sorry. Hold on 1 second. Sorry, I happen to be home alone with my kids, so I'm also keeping an ear out for them. I'm so sorry. I just heard something. I got to go check on them. 1 second.
If there are any questions in the meantime, I'm happy to attempt to pretend to be Peter and answer them. Oh, he's back.
Okay, sorry. No, it was my kids are young. They were screaming, but everything's okay. At least they say it's okay. All right, it's one of the problems with this year. Okay, sorry, where was I? Yeah, so this is being built in this shaft, this 100-meter long shaft. The folks at Fermilab who used this this is an access shaft in the neutrino beam. We only need a sort of small piece of it, small in the horizontal direction. You're seeing down the shaft here, and 100 meters vertically. And then we can make a 100-meter evacuated tube and run atom interferometers in it, like I was just describing. In fact, for example, run at 2 atom interferometers, 1 at each end, to look for gravitational waves across this baseline. And here you actually see some of the first cold strontium atoms in this trap here, that little dot. So that was very exciting. But as I mentioned, and as was brought up in the questions, it's not just MAGIS 100. Actually, a lot of people have gotten really excited about this effort. It's now become a worldwide effort. So there are many detectors now in Europe and in Asia. I've written out, I think, a few of the ones that are actually under construction now. So there is, for example, the Aeon detector in the UK. They'll be starting with MAGIS. We also started with 10-meter tall towers to sort of make sure we knew what we were doing at the 10-meter scale before scaling up to the 100-meter scale. So Aeon will start with a 10-meter scale, and they're actually working very closely with MAGIS. In fact, we're basically just directly collaborating, sort of like LIGO and Virgo. And as you know, having a network of gravitational wave detectors is very valuable for being more certain of your detections and learning more about the gravitational wave sources. So that would be the ultimate dream, that we have several of these detectors spaced around the globe, which will really improve our ability to search for gravitational waves. There's also the MIGA or MIGA detector in France, the Zyga detector in China. And these are all, you can see, around the 100-meter scale. They're using somewhat different techniques, but many of them are based on these clock atoms that I was talking about. And sort of they're different varying stages of construction, but all, I think, really happening, which is very exciting for me. So yes, so there you go. And the same basic ideas, same basic principles that I've been telling you for all of these. So did that answer the question about Aeon? Or are there any more questions? All right, excellent. So feel free to let me know if you have questions. So the sort of first step, of course, is building it on the ground. Ultimately, and this will have actually interesting gravitational wave sensitivity. I should say these first 100-meter scale detectors likely won't be able to get to the level of sensitivity we need to actually detect gravitational waves. They're, in the sense of as gravitational wave detectors, I think of them more as demonstrators, kind of like the same way the LIGO groups, like at Caltech or MIT, built these 40-meter long-ish, 100-meter long scale interferometers first to test out the technology before going to the full multi-kilometer scale. We'd also want to scale up these detectors ultimately to be sort of kilometer scale. And you can see, I haven't talked about it much, but for MAGIS, for example, and for Aeon 2, we tend to prefer to run these in vertical mode, meaning they would be down a mine shaft, and there absolutely are multi-kilometer long mine shafts around the world that appear to be suitable, good environments for this. Of course, we're learning a lot now by building these 100-meter scale detectors, so we'll know more about that in a few years when these are operational. The hope, I know the timescale for MAGIS the best, since I'm involved with it. MAGIS 100, we hope to be operational in ideally less than 5 years, taking data in under 5 years. based on the work with these terrestrial detectors, we'd scale up ultimately to the kilometer scale. Now, I should say, by the way, I said we don't expect to see gravitational waves. These will be, as I'm about to show you, these will be searching in a new frequency band. So we don't know what's there, right? I mean, you never know. That's the exciting thing about physics. When you're looking someplace new that people have never looked before, maybe there will be some very strong sources of gravitational waves, stronger than we sort of expect from known sources. And so maybe these could even see something, you don't know. And actually, as dark matter detectors, as I already mentioned before, these could potentially also look for dark matter and things like that. These are already going to be well past current bounds, so could potentially even, they are actually very good dark matter detectors. I'll get to that later on when I start talking about dark matter. We'd also like, however, to ultimately, farther in the future, consider satellite detectors for several reasons that I'll talk about. One of them is you can get even much longer baselines and go to even lower frequencies. And of course, for that, there are many plans now, for example, detectors like MAGIS or EDGE. This would certainly be leveraging all the technology that's being developed right now in these terrestrial detectors. Okay, so for my rest of the talk, when I'm showing you sort of science plots, I'll use science reach plots for MAGIS simply because I have those already. That's something I've been involved with. But you should keep in mind any of these detectors sort of is kind of broadly similar in science reach and how it works and things like that. Okay, any questions on these current efforts, on what's going on right now, or anything else that I've said? Okay, great. So here's our projections then for the strain sensitivity for future detectors, either kilometer scale on the ground, this black line here, or satellite based in space. You can see a little cartoon of a satellite detector. And this is on strain. Actually, I've plotted now strain per root hertz, but basically think of it as strain versus the frequency of the gravitational wave. And you can see LIGO and LISA for comparison. And maybe the first most interesting thing to note is that these detectors kind of naturally fall in this gap. Remember, I started this whole talk off by telling you about this frequency gap between LIGO and LISA and said we'd like to get in there. Well, these really high precision atomic clocks, atomic interferometer technology hopefully lets you get into that frequency gap. We can go below this seismic wall of LIGO, this very low frequency cutoff of LIGO, because these are excellent inertial proof masses that are not messed up by seismic noise and things like that because they're free falling. By the way, another thing to mention, the atoms are also excellent proof mass. Another reason you get below here is they're not messed with by much else. Proof masses have other things that happen to them. They get struck by atoms in the background gas, even at very low pressures. There is some background gas and that can jitter these proof masses around. We're talking about absurdly precise measurements here. That's a noise source for laser interferometers. They can get charged up. They can pick up tiny little bits of charge, and then the electromagnetic force is so strong that can be noise. The atoms luckily don't have any of that. If an atom in your cold dilute cloud of atoms gets struck by a particle from the background gas, by a molecule or an atom from the background gas, the atom just gets knocked completely out of the interferometer. It's very easy to mess up quantum coherence, right? In this case, actually, the atom would just literally fly out, not in the right place anymore, to even be seen. And it certainly would no longer participate in the interferometer sequence. It'd be moving the wrong speed to go through the beam splitters and things like that. These are highly Doppler selective. So that's actually not noise at all. It's sort of self-cleaning in that way. If you had too much background gas, you would destroy your whole ultra cold cloud of atoms. But so long as you don't do that, so long as you leave at least like half the atoms, you're good. You have no noise from that. Similarly with charging, atoms don't charge, or when they do become ions, that's such a dramatic effect that also they'll be thrown out and will no longer participate. So that's part of how you can get into this mid-band here, this frequency band between LIGO and LISA. You can see though that our future projection for the terrestrial detector, I've drawn this orange line and labeled it GGN. That stands for gravity gradient noise. One thing that does mess with the atom. So I said, okay, electromagnetic forces and stuff, we're pretty good at making them not mess with the atom. Actually, we do have to magnetically shield the whole tube and things like that. So it's maybe I make it sound a little easier than it is. It's certainly a highly non-trivial thing to do, but you can prepare the environment for the atoms in such a way that they really remain really pristine proof masses. But of course, one thing you can't shield is gravity. And it turns out the shaking of the Earth, while it couples directly to LIGO's mirrors, also couples to any proof mass gravitationally, just through Newtonian gravity. These are not gravitational waves now. This is just the, GM1m2 over r squared, Newtonian gravity. And you get these little wiggles, these seismic waves in the Earth. We're very familiar with them here in California. Although it might sound really small, right? They're very low amplitude. You don't see them with your eyes. They're there all the time, and they are moving some mass. And that actually acts gravitationally on these proof masses. And that puts a noise line here, roughly here. So you can see that will cut off any terrestrial detector at low frequencies. And that's part of why you want to go to space, to pick up even lower frequencies. Okay, let me pause for a second now and ask, this is kind of our key curve here. This is going to tell us, now I'm going to sort of move into what you can do with this, but are there any questions on this? Okay. Oh, I think we have a question. Yoni, could you unmute Stefan?
Yep.
Hi, I was just wondering what limits the MAGIS space at low frequencies. You kind of talked about it, what the terrestrial detector is limited at low frequencies. How is it for the space based one?
Yeah, that's a great question. Thank you. Yeah. There's of course a lot of details I'm glossing over with these experiments. And so you picked out a really important one, which absolutely. So let me think about the right way to say this here. Remember I was telling you that the atom interferometer acts in many ways as an accelerometer. It measures the acceleration. If you look at the accelerate, in fact, here, maybe I can even go back to this. Here we go. If you take two time derivatives of this, you can actually see it from here. If you take two time derivatives of this is the position change, right? But if I'm really viewing it as an acceleration, if I'm really measuring acceleration, two time derivatives brings out 2 omegas, right? Which means famously the effective acceleration of a mass, or the effective relative acceleration of two masses, I should really say, in a gravitational wave is HL omega squared. Okay. By measuring acceleration, we actually, if I can get there, we actually will then get cut off at low frequencies. You don't see the omega squared in these curves because I'm actually at high enough frequencies that it's flattened out. That's a detail. Let me not get into that. Actually, that's going to take us a longer discussion. But you do see it at low frequencies, and that will actually cut you off at the very least like omega squared, which is a fairly sharp rise. Then we actually, so that would be part of the answer to your question, that all the gravitational wave signals will get cut off like omega squared. But that wouldn't be this very sharp rise that I've drawn here. What's actually happening is that we go even one step further. We make this resonant. I told you we actually use a somewhat more complicated pulse sequence than I was showing you. We actually use a resonant pulse sequence. We hop the atom back and forth between state 1 and state 2. In time with whatever frequency band we want to look for. So for example, if I wanted to look, this is down at like 0.03 hertz or so, at a 30th of a hertz. So if I want to look for waves that are about 30 seconds long, then in space, I might hop the atoms back and forth at about 30-second cadence between states 1 and states 2. That's about as long as you can hold the atoms anyway. So it wouldn't be a very high Q resonance. I wouldn't move them back and forth very many times. So it would be quite a broad resonance, but it would cut off even more sharply than omega squared because it's semi-resonant. And so that's sort of, let's see, that's probably the best I can do without going into a lot of details. But so it actually cuts off fairly sharply, both because of the response to the gravitational wave, because that omega squared, and in fact, even a little sharper because we are somewhat resonant. It's not a very strong resonance, these low frequencies, but a little bit resonant. Did that at least kind of answer your question? Sorry, I couldn't.
Yeah, that was great. Thanks.
Perfect. Yeah. And different, by the way, different choice. This is one choice of parameters, but obviously we're not building either of these experiments yet. And certainly the space one would be many years in the future. I actually think this is sort of some things we did to illustrate it, but I think it's actually really interesting to think about all the different trade-offs you can make. Sizes of satellites, et cetera, amount of time you spend, which atoms you're using. And that can actually move these curves around to some extent. So these are really important questions. And when you get into it, you can sort of think, oh, which science do I want to look for? Do I want to look for things, do I want to optimize for things at a little lower frequency or a little higher frequency or what? So yes, good, great question. Actually, I also see a hand from Leonardo.
So yes, wouldn't the total duration of the measurement campaign also set a lower frequency cutoff, as in
Very good. That's right. Absolutely right. In principle, that's right. And I'm just assuming, you can see I've only gone down to, you know, like 100th of a hertz or a 30th of a hertz.
Mm-hmm.
We would be running these things essentially continuously. So you take one shot, and one shot on the Earth might only last a second or so, or in space, even limited by the lifetime of the strontium atom, might only be able to last about 100 seconds or so. But then you do another and another and another. So we'd actually have a very long measurement campaign. And in fact, the totals of all the shots that you run would be, you know, well, as long as, I mean, you like to keep going for years, or you know, something like LIGO, right? But you're absolutely right, that's in there. And also, actually, there is, I mentioned this rise of low frequencies. The rise does happen. Just another thing you might be asking is, there's this, different than the total runtime, which we want to be, you know, months like LIGO or something, that the time of each shot, of each atomic clock shot, that interrogation time that I was calling capital T before, might only be seconds or hundreds of seconds or something like that, limited by the lifetime of the strontium atom. That's actually what sets the corner. So that's what sets this frequency roughly. That's where this starts to rise. So did that answer the question?
Sure, yes, thanks.
Perfect. Yeah, great questions. Any other questions? Okay, great. Then I'll go on. Let me skip this. Okay, and let me just kind of very briefly show you actually some experimental demonstrations that already happened. This is now in a 10-meter test facility at Stanford that was already built some years ago as demonstration for many of these technologies. And they've been able to demonstrate a bunch of this. In particular, I mentioned we need extremely cold cooling. Well, here, this is real data taken in this tower. And the base, by the way, there are many other groups around the world who've done similarly impressive things. I was just using data from my colleagues at Stanford since I happen to be here and involved in this experiment stuff. There's a lot of other people who've done fantastic work too. But for example, they were able to set what was at the time a world record for coldest temperature in this dilute cloud of about 1 million atoms. This is real data showing that the atoms remained very tightly packed, which is what we want, even after long times. Long drop times, and that implied a temperature of about 50 picokelvin, which was already a couple orders of magnitude past the current record, and essentially where we needed to get for gravitational wave detection, which was very exciting. It was one of the things that made us think it's really possible to do this. This isn't just a crazy idea. And similarly, remember I mentioned that large momentum transfer beam splitter. Well, here's a cool experimental demonstration of that, a cool experimental realization of that from some years ago. This is also real data. This is a composite image stitched together. If you take a picture of the atoms, of course, once you take the picture, you mess up the interferometer, so you don't do that usually, but if you do decide halfway in the middle of the interferometer when the atom's wave function is maximally separated, right? Remember I said you beam split that atom, you split its wave function in 1/√2 here and here, right? And then you let that atom separate before you bring it back together with that mirror pulse, right? If you take a picture when they're maximally separated, here's what you get. They were able to rip apart the two halves of the atom's wave function 54 centimeters. Which was also a world record for most largest, you know, superposition state of a macroscopic object. Well, not really macroscopic, but of a macroscopic splitting, I should say, macroscopic superposition, macroscopic distance between the two halves of a wave function. Light, of course, has been split. Photons have been split over much larger distances, but this is for atoms, which is what we needed. So it's kind of cool quantum mechanics that you could even, you know, like walk between the two halves of the atom's wave function. But also this ability to split it farther and farther apart reads directly into your strain sensitivity. So this corresponded to like a factor of 100 boost to your strain sensitivity. And they're working now on going even farther, as I said, up to 1,000. So this was very exciting. And this is again a picture of the atom's wave function. You're seeing this density plot here. If the atom is localized on those two ends, the two halves of the atom's wave function are split very far apart. Okay, so those are some experimental, really cool results that the experimentalists have already demonstrated for this technology. Any questions on that before I go on? Okay, let me skip that. So now I want to ask, all right, what do we get by observing this midband? What do we see? And I'll just sort of give you a kind of preview. I think there's actually a lot more thinking about this that needs to happen because these detectors are just sort of starting to become realities now. We're really just starting to think about this now. People have mostly focused, for example, on science with LIGO or science with LISA, not as much in the midband because there hasn't been the possibility of looking for gravitational waves there before. Okay, so here's that sensitivity curve I was just showing you. What do you get? Well, here's a bunch of possible sources, for example, overlaid on top. This GW 150914, that's the very first source that LIGO saw, that famous 30 solar mass black hole binary pair. And you can see this is its whole lifetime extrapolated backwards, okay? So as these black holes go around and around each other, they actually near the end of their life, when they're in this frequency band, their dominant energy loss mechanism is gravitational radiation. So they're radiating gravitationally and falling ever closer together. And as they do so, they spin up. They go faster and faster. They orbit faster and faster around each other, right? That's what gravity does. That's what orbital mechanics does. And so they walk up this frequency curve, and eventually they entered the LIGO frequency band. They zipped across it in fractions of a second and merged. And of course, that's the famous story that LIGO saw. But before that, they were following this curve here. We can extrapolate backwards because it's just gravity. It's a relatively simple system. And you can see that these atom interferometer detectors would be sensitive to many of the sources, the same sources that go through LIGO, these black hole binaries, or for example, this blue line is a neutron star binary at 200 megaparsecs from us. So actually, you can detect a lot of the same sources in the midband, and even some new sources like white dwarf binaries. Okay. And again, these are just sources we know about, that we're sure these things exist, right? We've seen them. Of course, when you open a new frequency band, there may well be surprises, just like there was in fact with LIGO. So there could, for example, be heavier black holes that don't even make it all the way up to LIGO's frequency band, that merge before it. They might merge in this mid-frequency band, these intermediate mass black holes at hundreds of solar masses. We just don't know whether they're there because LIGO wouldn't have seen them yet. It has seen some surprisingly big ones, which I think gave a lot of people a lot of hope that there would be such even larger black holes. But even of the sources we know, there's a lot of interesting science you can get out of the midband. Now, what do you get? What do you get by looking at these sources? What do you learn? Let me point out just one thing, which is an important one. Here's your gravitational wave. These are the sort of phase fronts of the gravitational wave coming in to the solar system, and your detector is on the Earth here as it goes around the sun. An interesting thing happens. You may know, one thing we'd really like is to be able to localize these gravitational wave sources in the sky. We want to see where they're coming from. Well, this mid-frequency band gives you a huge boost to your ability to do that. So you've probably seen, or you may have seen, LIGO has these big error ellipses on the sky. You use the multiple different stations of LIGO to sort of try to triangulate where the source is coming from. But it still leaves, a reasonably large error bar on where that gravitational wave source is. And if you really want to do astronomy, if you really want to do gravitational wave astronomy, learn something about these sources, it helps to know where it is for a lot of reasons, actually, as I'll show you. Well, the midband gives you this huge boost, and here's how it works. Even actually with a single detector, and it's certainly better with a few, but even with a single detector, what happens is in this frequency band, this midband here, the sources live a long time. All these sources live months or years in this frequency band. Even though they only live fractions of a second in LIGOs, the remaining source lifetime is a strong function of frequency. So they live a very long lifetime in our frequency band, which means that your detector moves significantly around the sun in that time, which is sort of like having multiple different detectors spaced around the orbit of the Earth, okay? And then you can look to see when did this gravitational wave first hit your detectors, right? If the detectors are sort of here and here, this particular gravitational wave I've drawn will hit this one first and then this one. But if instead the detectors are here and here, the gravitational wave will hit them at the same time. And if you go through the little back of the envelope math for that, you can see that by measuring the timing difference between the phase advance as your detector orbits the sun, you get a boost. Not only can you resolve, normally any gravitational wave detector should be able to resolve this thing to about 1 over the SNR, 1 over the signal noise ratio of the detection, but you get a boost by L, the distance between your detectors, in this case, AU, over lambda, the wavelength of the gravitational wave. This can be a huge boost. This can be excellent because in the mid-frequency band, because L is AU, the wavelengths of the gravitational waves are like light seconds or so. Remember, we're looking at about the 1 Hertz band. So this ratio can be 10 or 100 or even more. That can easily boost your angular resolution. Even if you just have SNR sort of 1, it can easily get you to sub-degree angular localization on the sky, which is what you need. That's the field of view of big telescopes like Hubble. That's enough to tell your electromagnetic observing counterparts where to point their telescopes, okay? And then they can find the source within the field of view somewhere. So that's a real crucial threshold to get past, and this midband does it. And notice it doesn't work so well for LIGO because the sources don't last very long. It actually also doesn't work so well in the LISA band, in the 10⁻², 10⁻³ hertz band, because in that band, the wavelengths of the gravitational waves are longer. They are actually about AU. That's about the wavelength of the gravitational wave that you're looking for if you're looking about millihertz. So you don't get much boost to the angular localization there. This midband, it's something we realize this midband is really ideal for angular localization. Is that point clear? Are there questions on that? So that's kind of crucial to a lot of the science that you want to do. Okay, what can you do with this then? Well, one thing, for example, is observe these neutron star mergers. So you may know LIGO saw a neutron star merger. Here is a plot of when that neutron star merger was seen in gravitational waves and in all these bands of the electromagnetic spectrum, the gamma ray, X-ray, UV, and so on, versus time from the merger. And you can see, of course, famously, they got it in gamma ray early, but then in all the other bands, they didn't get it until much later, fractions of a day. Whereas the relevant dynamical timescale for neutron stars are about 10 kilometers. The speed of sound is about 1/10 the speed of light. The relevant dynamical timescale for neutron stars, when you want to learn something about the neutron star merger, about the equation of state, for example, is fractions of a second. So you really want to have your telescopes already turned, already on, already pointing at that source. The beautiful thing about observing in the midband, it's really complementary to observing with LIGO. You wouldn't see the merger of the neutron star itself in gravitational waves, but you would be able to predict where and when it's going to happen precisely enough that the electromagnetic telescopes can all turn and look at it. And of course, you learn a lot more about it too, not just its position, but also you learn more things about the source masses and things like that by observing more of the in-spiral, more of the waveform. And observing these neutron stars, as I mentioned earlier, we've already learned, things about they're the origin of these R process elements, these heavy elements like the gold and stuff in the universe. These are these exciting kilonova events. We learn a lot by observing these neutron star mergers. So there'll be a lot of exciting science to do in the midband that way. Even observing the same sources that LIGO is observing, it's very complementary. Any questions about that, about neutron stars? Another interesting source that can only be detected in the midband is white dwarf binaries. So you see here, I plotted a white dwarf binary at 20 megaparsecs. I should say, I'm sorry, white dwarf binary collisions. White dwarf binaries farther out, white dwarf binaries closer in are higher up this strain curve linearly, because the strain, like the amplitude of any wave, falls off linearly with R, right? So if they're only at 20 kiloparsecs, they're a factor of 1,000. So that's inside the galaxy roughly. They're a factor of 1,000 up here, and they're certainly viewable by LISA. But there aren't as many of them. So if you can look out to 20 megaparsecs, you can get a large enough number that the rate for mergers will be high enough that you get about 1 per year. So that's really where you want to get out to. That's the distance you want to be able to observe to see white dwarf binary mergers. The binaries themselves can be detectable in the lower frequency band, but only long before they merge. You'll never see the merger. The cool thing about the mid-frequency band is the merger can be localized and predicted in advance. And it will really be, you can see from this curve, the mid-frequency band is really the only way to see to ever see a white dwarf binary merger in gravitational waves. And that tells you a lot of neat things. You may know that, for example, there's actually been some controversy for a while about what type 1a supernova actually are. The sort of default to the standard theory is that it's a white dwarf which is accreting matter from a companion, and when it gets above the Chandrasekhar limit, it explodes, right? However, that doesn't look like it fits, at least not all of the type 1a supernova. It appears there could be, and this is still controversial, but there could be some population of them that come from other mechanisms. For example, one popular one that's been proposed is the so-called double degenerate mechanism, which would be, for example, 2 white dwarfs colliding from a binary. You would see that because, of course, in the supernova explosion itself actually looks quite similar, we think, whether it's 2 white dwarfs colliding or a single white dwarf. But in gravitational waves, they're extremely different, right? This is another example of the gravitational wave being a really unique source of information because it's coming from the mass, not the big explosion event. It's coming from these 2 masses orbiting each other. You would know immediately, was this event a white dwarf binary or a single white dwarf? And you learn a lot of things about that, and that that's what we're using currently as our standard candle. So it's pretty important to have better understanding, et cetera, et cetera. So we learn a lot of things from observing in the midband about white dwarfs as well. Any questions on that? Okay, so here's sort of a summary of what I've been telling you, which is that using this atomic technology, using these quantum sensors, lets you get it into this mid-frequency band below LIGO. It's very complementary to LIGO and LISA. And in fact, even when you're observing the same sources, you get a lot of extra information by being able to observe across as much of the gravitational spectrum as possible. We saw it could allow excellent angular resolution. You can identify upcoming neutron star and black hole mergers, allowing your telescopes to already be looking there to observe the event. This may even allow standard siren measurements. I didn't talk about this, but binaries can actually act a lot like standard candles. We call them standard sirens when we see them in gravitational waves. And you can do things like measure the Hubble expansion rate, measure distances and compare to redshifts, which gets you all of cosmology, right? We learn all about the expansion of the universe. You could potentially measure the dark energy equation of state, things like that. This is some very exciting work that's still ongoing right now. You can study white dwarf mergers. I didn't mention it, but you also learn things about black hole spins and eccentricities, which tells you more about these formation processes. You learn about these heavier black holes. And there may even be early universe sources of gravitational waves. These are more speculative, but also at the same time, if you see them, it's really revolutionary. Remember, I said in the beginning that gravitational waves are an excellent way to look at the early universe before the formation of the CMB. So sources like phase transitions, reheating, cosmic strings, etc., could well show up in this band, or that's why part of why you just want to cover as much of the gravitational spectrum as possible, and would be obviously very exciting. And in fact, as I said, I really likely expect surprises in every new band of the gravitational spectrum that we open. So I think there really will be a major part of the future of astronomy, astrophysics, and cosmology. And so it's really important that we observe in all possible bands, and we observe as much of the gravitational spectrum as we possibly can. So any new ideas are really valuable, and I encourage you to think carefully about are there new ways to look for gravitational waves? Okay, so I just wanted to pause for a second and ask, this is kind of the end of my first half of my topics. This is what I wanted to say about gravitational waves and quantum sensors as new detectors. Any questions? Any questions about any of this? I'm about to sort of switch topics in a pretty significant way and start talking about particle physics and cosmology. Yes, Leonardo.
Yes, so I had just a question. I would like a clarification on the angular resolution. So, so if I understand correctly, it would be sufficient to have one atom interferometer set up in order to achieve this delta theta resolution, as opposed to two conventional gravitational wave interferometers.
Yeah, you're absolutely right. That's actually that was actually one kind of point that we were making in this paper. We felt it was a pretty important point. Exactly, one detector that moves around the sun like this, that orbits, is actually in many cases equivalent to having multiple detectors. And I'd sort of guessed that ahead of time, but to prove that, we actually really did have to do the Fisher matrix and things like that. So we really checked the statistics to be sure that statement is indeed right. But you're right, exactly. And that's important. So for example, we don't necessarily want to build a lot of satellite detectors, especially, right? We saw we're hopefully building a few terrestrial detectors, although we can't, of course, space them across the orbit. So this point is still crucial. But certainly we don't want to build too many satellite detectors. They're very expensive. But the really nice thing is that you don't need it. You just need the one did that answer your question?
Yes, thank you very much.
Yeah, no, that's a great question. Actually, that's sort of a really important point. And notice for the detector, we really only even needed one baseline because of this way we have of removing the noise. And the cool thing that I didn't point out is that even with a single baseline, because the baseline, as it either is attached to the Earth and so spins or orbits around the Earth, it reorients, right? So that's part of what is helping you get your measure of both the polarization and angular location of the gravitational wave. That's part of what helps break all the degeneracies. Great. Any other questions before I go on to my next topic?
So Peter, I actually have a question, if you don't mind.
Please, yeah, of course.
So in terms of injecting a fake signal. So I think like LIGO doesn't actually wiggle their mirrors. I think they just inject a signal into the data stream. Is it possible for you guys to inject a signal actually physically as opposed to just electronically?
Yeah, great question. It is. There might be a couple different ways to do it. And so let me not, since we haven't yet finished building Magus 100 and things like that, a lot of these protocols aren't worked out. Or what isn't worked out is the best way to do it. But let me just say, probably the easiest way to do it, the first way you might think of, is when you shine these laser pulses. I describe them as just splitting the atom's wave function. The real answer for the phase shift calculation is much more complicated. You'd have to look in the papers written on this. The real answer is that the laser's phase also gets written onto the atom. So actually, they do this all the time. Actually, you can easily twiddle, you can easily tune the phase shift that comes out of any atom interferometer. Just simply by turning the knob, changing your laser phase, which that's an easy control parameter for the experimentalist to change. So they can absolutely inject any kind of oscillating or funny phase shift you want into the experiment just by changing the laser's input phase, essentially. So that's probably the easiest way to do it. There might be other ways too.
Cool, thanks.
Yeah, absolutely. No, and it's a great question. That's important, and there's sort of well, there's lots of important questions, a lot of which we haven't solved yet. I mean, there's, like we said, we're building this demonstrator now, so there's a lot of these things that are really, still to be kind of actually figured out, actually worked out experimentally. Yeah, great. Any other questions before I go on to the second half of my topics for these 3 lectures? Okay. Great, just give you another minute or something. Okay, let me go on then. So we were just talking about gravitational waves with atom interferometry. Now I want to move on to what I think at first sight anyway is a very different question, which is how can we learn more about some of these deep, really important open questions in particle physics and cosmology and things like that from these quantum detectors, from these quantum detection techniques. Actually, as I already gave you sort of a preview, it's not as different from gravitational wave detection as you might think, and I'm going to try to go through that. Okay, but to begin with, let me go back to my notes on my iPad here. So sorry, give me just 1 second. I was having some technical difficulties there. All right. Okay, sorry. Okay, good. Hopefully that's working. Hopefully you can see my screen now. All right.
Yep, we can see.
Perfect, thank you. Okay, so now I want to kind of shift gears. I was just telling you about some actual experimental technologies really happening, things being built. Now I want to shift back to some more theoretical questions, theoretical concerns. What are, and I actually wanted to start by kind of giving you a broad overview. I know different people have very different backgrounds here. So some of you sort of may already be aware of this, but I think it's very important for everyone to get a kind of a broad, big picture overview of just what are our open questions. And I'll of course tell it from my point of view. I think every different theorist would tell it from a somewhat different point of view. Luckily, as Yoni said, he and I tend to work on similar things, so at least he probably won't disagree too violently with me, and no one else is on the call. So no, but everyone have a different point of view. But here's sort of roughly kind of a big picture. What are our big open questions? What do we still want to know in, let's say, particle physics or high energy physics or whatever you want to say? We have to start. I hope you've heard before at our standard model of particle physics, our understanding of all the, we know the quarks that make up the nucleons, we know about the electron and the muon, all the fundamental particles, the fundamental fermions, and we know they interact through electromagnetism and gravity and the strong and weak nuclear forces, blah, blah, blah. That all is beautifully encapsulated in the quantum field theory of the standard model. Hopefully you've heard before that works just incredibly well. That really describes essentially every lab experiment we've ever done, with perhaps a few open anomalies. but basically every lab experiment, every measurement at the LHC and all the previous colliders. So it's really amazing. So you might ask why. However, we spent a lot of time talking about new things beyond the standard model. Why is that? And I would really divide it into kind of two classes of reasons. For thinking about physics beyond the standard model. The first class of reasons, and by the way, feel free to interrupt me at any time. This is certainly something people could disagree about. So if you want to disagree or have a question or anything, go right ahead. The first class of reasons I'd characterize as saying we actually have some observations that just require it. Some observations just require new physics beyond the standard model. I said all the lab experiments are consistent with the standard model, but for example, all of our observations that point towards dark matter, they really require new physics beyond the standard model. Okay, that's actually, let me just pause there for a second. That's actually a point that's sometimes not appreciated by many people outside the field. We really know enough now, I would say, about both the standard model and the history of the universe, of cosmology, to really say that with all these various observations, the standard model does not explain them. So I mean things like the rotation curves of galaxies, right? Hopefully you've heard galaxies are spinning too fast to be held in just by the Newtonian gravity of the matter we see. Or the bullet cluster. If you don't know about that, I strongly recommend looking it up. I won't go through it, but basically we can use gravitational lensing to tell us about the mass that's there, and it really does not look like again the mass that we see, or even like it's coming from the mass that we see. And in particular, actually, our measurements of the CMB really give us very precise measurements of the contents of the universe. And again, it really looks like there's things beyond the standard model, and we know enough about the standard model to know that it just isn't possible for the standard model rules themselves to explain it. Now, it could be that it's still logically possible. There's things like a modification of gravity, but that, of course, is new physics. So that's all I mean by this. I mean, these observations require something new, some new physics, some new fundamental laws of nature that we haven't learned yet. So that's what makes us all very excited about dark matter. That not only is it the major, most of the mass in the universe, which already, that's cool. We want to know what that is. But it's definitely some new piece of the fundamental laws of nature that we do not know yet. Okay. The other main thing that goes in this category, I would say, is what we call baryogenesis, or the origin of the matter-antimatter asymmetry, basically why our universe is filled with matter and has very little antimatter. That does not come out of the standard model. There has to be something new to explain it. Either of these things actually could be explained by physics going on either much earlier in the universe or much later. I really don't know. We don't know what the physics is at all, but there has to be something. Okay, so I'm going to focus mostly on dark matter, but I did want to point out this second class because I think it's very important to just keep it in mind. The second class of reasons for thinking that there's new physics is that the parameters of the standard model look funny, okay, in some way. And this would be funny in some way, which strongly suggests, but does not logically absolutely require new physics beyond the standard model. So this first class says there actually has to be new physics. The second class, things just look really weird if there isn't new physics. And I won't talk too much about these, but for example, parameters like the cosmological constant, the observed value, let's say, of the dark energy in our universe, or the mass of the Higgs boson, or something I will come back to later, probably next lecture, the value of what's called the strong CP angle, which is essentially the measurement of the electric dipole moment of nucleons. All three of those parameters look really funny. Actually, all three of those parameters are much smaller than you would have thought they should be. And then finally, also, I would include in this class the masses of the fundamental particles. The masses of the quarks and leptons seem to have a sort of pattern to them. At least many people have seen patterns in them over the years, but we don't know why that would be, why they come in generations, why 3 generations, things like that. Okay, let me pause here and just say, are there questions or objections? Okay. And I just wanted to give you, although I won't focus on it too much because it is so important, it's influenced a lot of thinking about physics beyond the standard model. I just wanted to give you a kind of a brief explanation of what I meant by the tuning in particular of these three parameters. And like I said, we will actually come back to the strong CP angle. Let me illustrate it with the cosmological constant, though, because I think that's a little more clear, a little more intuitive to people what it means anyway. There are, to say it very sort of cartoon picture, there are three what we think are very basic fundamental scales in nature or in the standard model in our understanding so far, which is the Planck scale, the electroweak scale, and then I would include this scale of dark energy, at least for right now. The Planck scale is around 10 to the 19 GeV. This is the scale at which quantum gravity has to kick in. So at energies above that or distances shorter than that, we know our theory actually is wrong. Actually, that's something I didn't say in the previous category, but it's certainly true. The electroweak scale is around 10 to the 3 GeV. That's the scale being probed by the LHC. And then the measured value of the dark energy density is around 10 to the minus 3 EV. Okay. And it turns out that explaining why this number is so much smaller than these other two, and actually let me focus on the sort of smallest possible problem is why this one is smaller than the next higher one, the electroweak scale. Turns out that explaining that is rather hard. And the reason is as follows, and if you haven't seen quantum field theory before, you're just going to have to accept this, okay? But I just want you to get the sort of basic idea. You don't have to know exactly where it comes from. The basic idea is that the cosmological constant, which is a vacuum energy density in our universe, I'll just write it as the CC, the cosmological constant, a uniform background energy density. We actually, by the way, don't know that the dark energy is a constant, but the cosmological constant definitely has to be less than or equal to this amount. So this definitely has to be less than or equal to this milli-eV. And in fact, it's usually written as an energy density. So that would be an energy to the fourth in our funny units of H bar and C are 1. It turns out there are contributions to the cosmological constant, okay, that are much larger, that come from, for example, this scale here. So writing it as an EV, this 10 to the 3 GeV is 10 to the 12 EV, and it's an energy density, so it's to the fourth. You calculate these as loop diagrams, for example, in quantum field theory. Let me not go into that. The point is that quantum mechanics gives contributions to this cosmological constant of this size, which is way bigger than the observed value. So what's going on? That looks like it's ruled out. Well, it's not that it only gives one contribution, actually it gives many, and they can be of opposite sign, so they certainly can cancel, but they're all of about the same size. So you see, they have to cancel. This is, if I write this out, you can see this is two numbers that are around 10 to the 48 in these units of EV to the fourth. And they have to equal the CC, which is about 10 to the minus 12 in this units of EV to the fourth. Okay, all this times EV to the fourth. So that's an absurd cancellation of like 60 digits. These two numbers have to be equal to 60 digits. The thing you have to know about them is that they came from totally different parts of physics, totally different kinds of physics gave rise to these two numbers. At least they're parts of physics that appear to be totally different in the standard model. So why should they be equal to 60 digits? I mean, it's possible, but it looks like a tremendous accident. Okay, that's this fine-tuning problem. The CC is probably the most dramatic fine-tuning problem. I'll actually talk a little bit later about this strong CP problem, but it's the same sort of thing. Okay, are there any questions on that? I should get out the chat. Okay. Or any questions at all on this, my sort of reasons for thinking about physics beyond the standard model? I think it's useful to keep this kind of big picture in mind as we go through the rest of the lectures, and just useful in general.
I'll just say for the record that I don't object and I agree with your ordering.
Excellent. All right. I figured you and I would be on the same side on this. Okay, great.
I guess, by the way, one could also put neutrino masses.
Yeah, absolutely. Absolutely. I think that's totally fair, whether you call them, yeah, a new part of the standard model. Absolutely. We don't know what gives rise to them. Absolutely. Yeah. And I should put quantum gravity too, for sure. So let me put ... Let me put dot, 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 since there's a few more things, definitely. Yeah, great, thank you. Yeah, other comments, questions? Okay, good. So now, though, I want to move and mostly focus on dark matter. Otherwise, as I said, we'll actually be informed by these tuning problems as well. Okay, so let's see. In the time I've got remaining, I kind of want to just give you an introduction to thinking about dark matter direct detection, and then we're going to pick up next lecture tomorrow, and we'll talk about some more details. So try to remember what I'm telling you now. That'll be very important for tomorrow. Okay. So we'll pick up tomorrow and talk about details of how you might actually do some of this detection. Okay, so dark matter. So I said we know for sure there's new physics beyond the standard model. But what we don't know is at all have really any clue what it actually is, any experimental clue, I would say. In particular, if we think it's some new particle that's cold and non-relativistic and clumping and forming structure and things like that, it would have a mass, but we really have no idea what the mass is. I'll draw a very long spectrum here. The mass could be anything from 10 to the minus 22 eV, the mass, in fact, of the dominant component of dark matter, could be anything from 10 to the minus 22 eV, all the way up to the Planck scale, 10 to the 19 GeV. So that's already a lot of orders of magnitude, 50, 60, and beyond even. In fact, for example, primordial black holes would be a candidate that's even heavier than the Planck mass. If it's a fundamental particle and it's heavier than the Planck mass, it probably has to be a black hole, probably. But primordial black holes, you may know, can even in certain mass ranges be good dark matter candidates. Okay. This is a huge range, and in particular, it's a huge range to go looking over. The sort of famous example of the weakly interacting massive particle, the WIMP, would be around 100 GeV or so, give or take, with some uncertainty, of course. And that's certainly a very motivated thing to look for, that there's been a lot of excellent experimental effort on looking for. I won't talk so much about that because I think a lot of the techniques for that are well established, although there are actually a lot of new exciting ideas. It's just I can only cover a finite amount of things. Down at much lower masses, the sort of most famous candidate is the axion. Okay, I am going to talk more about that. I will talk about the lighter masses. But in particular, I kind of wanted to, for the thinking about the purposes of direct detection, I kind of want to divide this mass plane for dark matter here at a mass of very roughly 10 eV or so, the big twiddle. And the reason is the following. Okay, the local density of dark matter, local means around us in the galaxy, we've measured to be roughly about 0.3 JeV per cubic centimeter. So if the dark matter was in particles of mass 0.3 JeV, there'd be about 1 per cubic centimeter around us. And if I cast this in my favorite units, where I convert all the centimeters to energies, this uncertainty principle conversion, it's about 0.04 eV to the fourth. Okay. The reason then that I want to divide this mass spectrum for the dark matter here is that for these heavy mass dark matter particles, you can see that they act very particle-like. WIMPs, there's sort of about 1 and about this amount of volume, for example. You can calculate that from this mass density. And they're just these tiny little particles, very well separated. They act like these tiny little billiard balls flying around. So I'll call them particle-like dark matter. And there we have an idea what to do. We look for a single hard particle scattering. So we look for the dark matter to come in, smack off some nucleon, for example, give it a hard hit. And then, the dark matter bounces off. That's not what you see, but the nucleus bounces off, and you can look for scintillation light from that, or ionization, or whatever the signals are in the different detectors. However, most of these WIMP detectors, at least the traditional WIMP detectors, have thresholds around a kiloelectron volt or so. People, by the way, it's an very active area of research to keep pushing that down. Because you can see that sort of limits the smallest mass you can go looking for for dark matter. If the mass was around a GeV, something to keep in mind is that the velocity of dark matter, the virial velocity in our galaxy, is around 10 to the minus 3. That's unitless because that's of C. C is 1, remember? So it's 10 to the minus 3. That means the kinetic energy is V squared times the mass. So it's 10 to the minus 6 of the mass. If the mass is a GeV, 10 to the 9 eV, then the kinetic energy is about a keV. That's about the lightest particle you could look for. So you can see if you want to go much lighter, of course, you want to push the threshold down, and there's a lot of exciting work on that. I won't talk about that simply for reasons of time. Instead, I want to focus on this lighter part of the mass plane. And if you're sort of thinking about putting the threshold down, it starts to, at least for conventional detectors, it sort of looks hopeless to go looking for individual particles down there. So how can we do it? Okay. And here I just want to start by, so I'll really tell you tomorrow's lecture how we think about doing it. But I want to start by giving you a picture right now of what does this dark matter look like. Okay. So I want to call this dark matter kind of field-like instead of particle-like, or sometimes it's called wave-like instead of particle-like. And the reason is the following, and it's also tied up. I didn't tell you yet the reason why there's this lower cutoff, but I'm about to in a second. The reason is the following: when the mass of the dark matter gets very light, its wavelength gets very long, right? That's the way quantum mechanics works. So instead of being an individual little particle, you should think of it as some chunks, some wave packets that are kind of flying around our local galaxy. And here are the individual particles. Instead of being individual little dots flying around, there are all these particles here, but they're quite big. Okay. It's really the de Broglie wavelength you should think about. So the de Broglie wavelength, which is 1 over the momentum, is 1 over mv. Since this v is 10 to the minus 3, it's about 1,000 times 1 over m, about 1,000 times the Compton wavelength. At least locally in our galaxy. That's also what sets this lower cutoff. If you get all the way down to these extremely small masses, this has a de Broglie wavelength, for example, in a dwarf galaxy, which is about the size of a dwarf galaxy. Any lower, the mass would be, if the mass was any lower, the wavelength would be longer. They wouldn't even fit. They couldn't collapse and form. They couldn't gravitationally collapse and make dwarf galaxies. And we've seen dwarf galaxies, which are dark matter dominated. So that is why there's this lower cutoff on the dominant component of dark matter. Let me pause there and say, any questions on that? This is kind of a crucial idea for everything that comes next. Okay. So one sort of important thing that happens then is as the mass gets very low, these particles get very light and they start to overlap. There starts to be more than one of them per de Broglie wavelength cubed. Okay. You can in fact calculate that. Right, I can make a little cube which is of size the de Broglie wavelength here, and then I could calculate, okay, the number of density of the number of dark matter particles per this let's call this lambda, per lambda cubed, is of course the mass density of dark matter divided by the mass of dark matter. That's the number density of dark matter, and then times the volume times this lambda cubed. That's how many particles there are per de Broglie wavelength. And if you work it out, if you just use those little numbers and formula I've just given you, you'll find that this is about 10 eV over the mass of dark matter to the 4th, which is why I divided this mass plane around 10 eV very roughly, because below that, that's where the phase space occupancy of dark matter starts to become more than 1. Also, you know, at that point, it can't be a fermion for sure. It's going to have to be a boson, right? Since I can't put more than 1 fermion, maybe 2, in a quantum state. Below this, you can see at masses below this, the phase space occupancy gets large quite quickly. So down at the lowest masses, there's a ton of particles per de Broglie wavelength cubed. In fact, at that point, it's often easier not to think of them as individual particles, but to think of them as some coherent field. Okay, just put them together because they are so heavily overlapped. Their phase space occupancy is so large. For many purposes, they just act like a classical field. Okay. So now let me see if I can make this work here. If I can get back to my slides. Okay, so the picture then is, so hopefully, yes, you're seeing that, good. The picture then is, instead of lots of little individual particles zipping around the galaxy, it's just some coherent field, like a coherent maybe magnetic field or electric field filling the galaxy. If it was a vector, if it was a spin 1 boson, or if it was a scalar, it's just some number, some scalar field, some number at each point in space. But then, as I'll show you in just this minute, it will actually be, these fields will be oscillating in time. In fact, they'll be oscillating with frequency equal to the mass of the field. And it's very often very useful to picture these things as a coherent oscillating field that can kind of tell you how to go looking for it. And actually, I just want to kind of pause right here and point out, we'll really talk about detection tomorrow, but I want to point out already, look, now this picture of dark matter is a lot more similar to a picture of a gravitational wave, right? Looking for this, maybe you can imagine that looking for this actually looks a lot like looking for a gravitational wave in many cases. It's some background field propagating through you. It's coupled to you very weakly, right? We know we don't talk to the dark matter very strongly, so you're going to have to make some very high precision experiment to look for it. But when you do, you'll see this field that penetrates all things, goes right through the Earth, right through your shielding, blah, blah. And you're looking for your signal is some very weak coupling to whatever your high sensitive detector is that's oscillating in time like this, okay? So hopefully that's clear why this might be similar to gravitational wave detection. And in fact, I'll show you tomorrow some explicit examples of how, for example, the kind of gravitational wave detector I was telling you about earlier when we were talking about atom interferometers can actually also be a dark matter direct detection experiment, okay? So I think that is probably a good place to stop the lectures for today. And let me ask if there are any questions. I'm also happy to stick around I think there was some extra period left, or there isn't anything officially scheduled, but anyone who wants to stick around is welcome to stick around, and I'm happy to answer personal questions or anything. I mean, individual questions. So let me stop there and ask, are there any questions about this kind of picture of field-like dark matter? Yes, from Stefan.
Hi, thanks. This was all very clear and very nice.
Thank you.
I have a question about the motivation that you discussed before. Mm-hmm. So generally, I think I agree very much with what you have shown. But I mean, the most discussion I think is going on about this like second point, what you have like kind of mentioned a little bit, I think. So they are like, instead of saying, oh, these parameters are funny, we have to fix them somehow, you can run like an anthropic argument saying, oh, but if they wouldn't be so funny, we just wouldn't be here, right? So this is the typical way it goes, and like how people try to argue against it. And for example, the axion is very much motivated by an argument like this. So I'm just wondering, how much do you see like the danger of theories being blinded by this motivation, not to look in other, let's say, funny spots that could maybe even still be the dark matter, and the solution to this funniness is something completely else?
Good. Yeah, that's a great question. That's a broad question. There's probably a lot one could say about it. Let me just say maybe a couple of things, and that feel free to chime back in, or anyone else. Absolutely. So that's right. We've often historically thought of what we call dynamical solutions to this, or things that make these parameters seem not funny. But absolutely another option, right, is this landscape, maybe with these anthropic arguments, saying, yeah, there's just a lot of different, there's a lot of different possibilities for these fundamental constants, and we happen to live with these values in some piece of the universe that has these values, just because that's where we are, because that's where it's possible. So you sort of say, okay. And there's certainly plenty of arguments for arguing why things would look very different if any of these parameters were different. Absolutely. And I think those sort of arguments should be taken very seriously. I've spent a lot of time thinking about anthropics and the multiverse and things like that in my career. A flip side, I think it's fair to say, and I include myself in this, that every time someone has tried to make these arguments more precise, and myself included, it really sort of fails. I mean, you can try to make, and this cosmological constant was perhaps the best example. Weinberg started that many years ago. But every time people tried to actually explain why, oh yeah, we couldn't have lived with a different value, you always have to, for example, with the cosmological constant arguments, you always have to decide, well, I'm only changing the cosmological constant and no other parameters, or I'm only changing these few and none of these others. And And no one's ever been able to make an actually sort of, rigorous, like with equations and numbers argument kind of from first principles. That doesn't mean it's not true, right? I mean, if you spend some time thinking about these things, you sort of immediately realize how challenging it is to think about these things. But I would say I just don't want to accept it right away. So it's absolutely something I think is worth keeping in mind, but I would also want to keep in mind the possibility of these other dynamical type solutions. I think it's just important to keep both in mind. And so that's a very important question. Thank you. It's important to bring that up.
Thanks.
First, is that fair? I mean, would you agree with that?
Yeah, totally. I think, I mean, I'm more from the experimental side. I'm more worried kind of that, if you take this motivation very serious and you say, okay, I will want to try a theory that is beautiful, that you kind of suddenly miss a less beautiful theory, which in the end turns out to be the true theory, but we just didn't look at it because it was not beautiful.
That's very well. That's an excellent point. That's perfectly said, and that was exactly the next thing I wanted to say. Exactly as you said. You said it very well. Which is exactly that. Actually, I completely agree. So while I spend some of my time thinking theoretically about solutions to these problems, that would be natural, would appear not to have tuning in them. I also think it's very important. In fact, what I do with a lot of my time, as you probably noticed, is spend time thinking of new experiments, because I think it's very important that we just cover as much space as possible. So what I'm really going to tell you, in fact, when we, for example, go through the story of dark matter, is that I want to cover this whole thing, in a sense, independent of theory motivation. So although the theory motivation for the axion might pick a particular mass range, I'm actually going to try to say, can we cover the whole mass range? And same with WIMPs. Maybe the particular theory motivation zeroes in a particular mass range. I actually think we should cover this whole thing. And that's an example in dark matter of this general point that you're making, which I couldn't agree with more. It's really an important point that I don't think we should be blinded by theory prejudice. So that's why it's very important to always remember, while these appear funny, they are not either logical inconsistencies or mathematical inconsistencies with a theory, nor are they violations of any experimental result, right? And so maybe that's just the way the theory is for one reason or another, right? And so absolutely, I definitely strongly believe we shouldn't, when we're experimentally looking, we should not be too prejudiced against this. We need to keep an open mind. Now it's it's a trade-off. Let me just say, since it's sometimes actually it's it's really important question. Where should you put your effort, right? Where should you put your dollars? I have good friends who are experimentalists. They don't get to make too many experiments in their life, and they want to discover something new. Where should they put their time? One of the things I like to say is, I think it's important not to be too blinded by theory prejudice, but at the same time, we do know a lot about the standard model. So for example, I wouldn't be, to quote, I think it was Woody Allen, so open-minded your brain falls out. There are sometimes signals which appear very difficult to get in, say, any quantum field theory based on the standard model, or at least there's no math that gives rise to them, when there isn't a theory at all. If there's a theory, but it's tuned, it looks funny in some way, sort of, I'm okay with it. I think you should look, but my own personal, where I draw the line, and different people can draw the line different places. You can all tell me what you think, but where I draw the line is, if there's no theory at all, then I usually really feel that may not be worth trying. There probably even be exceptions to that, but that's usually where I draw the line. And I should say too, I usually take the tuning maybe as some motivation. So I'll tell you in the next lecture, I'm a little more motivated to look for the parts of the dark matter parameter space which say solve the strong CP problem, but not completely motivated to only look there. In fact, I think it's very important. In fact, I'm heavily involved with experiments that look other places. Spend a lot of time working on them and proposing them. So while maybe there's a little bit of a sort of accumulation of motivation or something in those parts of parameter space, I really think it's very important what you're saying, that we don't get too prejudiced. Is that fair? Would you agree?
Oh, that's perfectly great. I mean, I think this 100% resonates with what I would say. Yes. Thanks.
Perfect. Yeah, that's a great question. Actually, that's one of the real reasons I wanted to start with talking about this sort of very big theory overview. So thank you. Yeah, that's why I think it's really important for everyone, including experimentalists who are building the individual experiments, to be aware of the big theory overview and think for themselves about where do they want to look.
Yeah. So I think from an experimental point of view, it's often the question, like, where do you stop doing your experiment, trying to make it more sensitive or explore other ranges? And I think it should not be where like the second motivation does not exist so strongly anymore, because you still have the first one, and that's actually the physics motivation why you want to search something, right?
I completely agree. I completely agree. Absolutely. Yeah, excellent. Yeah, it was a great comment. Any other comments, questions, disagreements with me?
Can you comment on the perturbative aspect of quantum field theory that we only started seeing some effort to kind of build the mathematical rigorous foundation of it, but is there a possibility that maybe we have to go beyond Feynman path integral to kind of see something new?
That's a great question. Yeah, it's certainly possible. Now I'll say this. Oh, by the way, sorry, I should interrupt myself. We're definitely well into the extra time here. Obviously, any of you who need to leave should feel free to leave. But I'm happy to just stick around and keep answering questions. Or
maybe
keep
actually, so
chatting
Peter, I might have to head in a minute. So but maybe before answering that question, let me just say two things. So number one is that we will have a question and answer session, which I will be leading at 9 a.m. Central Time tomorrow morning. And in terms of that, Peter, if you could post your slides somewhere so that we could sort of look at them, so I could pretend to be you for those 15 minutes.
Yeah, absolutely. Do you know where? Is there a place I'm supposed to post my slides?
I mean, if I don't think. I mean, we can make a page on the webpage, but you could also like put it in a Dropbox link or something, and then we could. Yeah.
Okay, I'll try to do that. Yeah.
Sorry, I interrupt you. Sorry. In fact, if you got the email with the instructions, there should be also links to a shared folder where there is a specific document just for you. So where you can put link to the slides or whatever material you want to add, and also the students can write their questions later on, maybe if they come up to their minds in that document. So if you don't have that link, just write me and I will send it to you again. But you should have it in the main email that has been sent a couple of days ago.
Good. Yeah, I think I've got that link, and then I'll look for a place I can post my slides.
Okay.
Thanks so much, Peter.
Perfect. Yeah, and Yoni, feel free to take off. If you could just make me host, then no problem. I can do the questions. Okay, great. Yeah, sorry. So what was I saying? So yes, right. So absolutely, there could be. Now one nice thing is that, for example, in particular, to explain, let's say, dark matter, which is something I'm going to talk a lot about, or baryogenesis or anything, you don't need to go beyond our sort of current understanding of quantum field theory. That doesn't mean that's not what's going to happen ultimately. But let's say, I think for myself and many people, you look around and say, wow, the standard model was really successful. I mean, we explained so many things. We see so much about our world just beautifully explained that way. It seems like the sort of simplest thing to do is to extend it by adding some dark matter, or extend it by adding something that does baryogenesis, or inflation, for example. There's strong evidence for inflation, things like that. And all of that fits within quantum field theory. Of course, the one thing that doesn't fit famously within quantum, at least no one's ever made it fit, is quantum gravity, right? Is above the Planck scale, unifying the two. But let me just actually, this may not have been exactly your question, but let me just take a minute to say the following thing, which is actually something that a lot of even practicing senior physicists, my age and older, maybe who just don't do high energy theory, are not really aware of, which is you only need a theory of quantum gravity. You only need it above this Planck scale. So when you're at higher energies, in other words, shorter distances. So if we ever made a collider that could go up there, for example, which is not going to be in any of our lifetimes, but then you would need a theory of quantum gravity to describe what's going on. At our much lower energies that we live at, you don't need it even to describe gravity. We have a perfectly good low energy effective field theory of gravity and quantum mechanics. A quantum field theory of gravity, no problem. You can look at papers by, for example, Donahue, I think. So it works great at every energy scale we've ever probed. Everything works great, including with gravity. And that's part of why we're hesitant, I guess, to go beyond quantum field. That's part of why most of what we do is think, okay, look, dark matter is easily explainable within the theory that already works great. But yeah, it could be. And we certainly know by the time you get to the Planck scale that you have to have something like a string theory, which is, say, for example, which is similar to a field theory, but is not the same. So that might have been one aspect of your question. Another aspect might have been just about perturbativity or not. There are certainly times where you have to work in non-perturbative methods, actually even with the axion, for example. We won't discuss it much, and that's very important. Doing all those kind of calculations are very important within the framework of quantum field theory. So did that address your question at all, or was that what you were asking?
Perfect. Yeah, that was. Yeah,
great.
Thank you so much.
Good. Yeah, great. Any more questions? Yes, Leonardo, can you unmute yourself, or do I have to do it? Okay.
I'm unmuted. Yeah. So I had a question concerning the effectively the wave-like behavior of ultralight dark matter. So
good.
Right. So if we take the wave-like behavior, then we would expect approximately, say, a scalar dark matter field to be described in terms of some cosine function. And in this case, if we want to describe the collection of waves, it would be a sum of all such waves.
Yes.
So this would imply that there are regions of destructive interference within even a halo. So presumably, that would imply that there exist regions where the effective density is so small that possibly the wave-like description would break down. So let's assume, for example, that there is some Earth-based experiment that is looking for such wave-like dark matter behavior. Would this formalism of just writing down the expression for the field in terms of sum of cosine still be valid, or should there be some modification, for example, in terms of coherent states or any sort of?
Yeah, great. That's a great question, and actually touches on a bunch of different things. So let me see. Let me answer a couple different things. So first, great question. You're absolutely right. There can be regions of much lower density. However, it turns out, it's funny, but so you're familiar with this from quantum mechanics that, particle versus wave, of course, really they're not, I mean, they're all the same, right? Really, they're the same thing. And we just handle them consistently in quantum mechanics as you're used to. And in particular, actually, you can see this from the particle perspective. So I'll jump back and forth, which I know can be a little confusing. Sorry about that, but you can sort of see from the particle perspective. Absolutely, right? The galaxy is a big place. You look around, there's some average density. I've written it here, or the number density, or the let's say the number per de Broglie wavelength cubed. I've written here. That's an average, right? But it'll certainly have fluctuations. When m is close to 10 eV, then you can see there's about 1 particle per de Broglie wavelength cubed, and then you should expect quite large fluctuations, right? Order 1 fluctuations, just thanks to Poissonian fluctuations. And so then there absolutely is this kind of breakdown of this of a classical field picture way of looking at it. And then you definitely do want to go to a sort of more, well, definitely it's too strong. Then for some questions you may be asking, you need to go to a more discretized picture. You actually go to the particle picture, and you could, for example, do into there. That's where it sort of walks over into this more particle-like thing. That's kind of the edge of my regime. And you could calculate individual particle scattering. And absolutely, there would actually be an edge. So imagine I had something that could tune into the background field, a radio, for example. As Yoni mentioned, we called one of our experiments DM radio because it is sort of tuning into the background field, and you're measuring it. If it was able to measure these high masses, which it isn't, but if it was, you would, at low masses, it looks like a radio wave, like some background oscillating cosine, and it would look quite perfect, right? But if I measured it really, really precisely, far more precisely than we're going to be able to see the dark matter, really, really precisely, or if I could measure at higher and higher masses, which I can't do with this experiment, but imagine, right, theorist experiment, then I would start to see it kind of breaking up. It wouldn't be a perfect classical cosine anymore. In fact, it would be more like particulate, more like chunks. And of course, well past this, it breaks up into individual events. So absolutely, there is that boundary you're describing. Now, however, for the lightest masses, you can see this number becomes gigantic. And so the odds of ever finding yourself in a cube, maybe somewhere in the galaxy there is, but the odds of the one sample that you take on the Earth here, the odds of finding yourself there can become incredibly small. Imagine this is 10 to the minus 22 eV, this is 10 to the 23 to the 4. That's a lot of particles. So it'll just never fluctuate to 0, or even never fluctuate down very much at all. But you can see it's absolutely a function of mass. So the behavior you're talking about absolutely happens kind of around this gray area. And I'll sort of stay away from the gray area in my lectures, but it's actually a very important point. You kind of, so this is something I won't say, but you're kind of trying to push there from above and from below. You're kind of trying to push the techniques that work down at these low masses up, and you're kind of trying to push the techniques that work at the high masses down. And well, it's a separate talk. We're making some progress on it, but there's absolutely a lot of open work left to be done. So yeah, did that answer the question, at least kind of?
Sure, yes, thanks.
Yeah, that's a great question. Any other questions? Yes, Mackenzie, can you unmute yourself, or do I need to?
Okay, I think I can unmute myself.
Okay, good.
I was unclear how the atomic interferometer works to detect dark matter. Is it that the axion is like producing some sort of particle to interact with the atoms?
Good, great question, actually. I haven't told you that yet, although I've sort of hinted at it. In fact, I'll really walk you through it a little bit tomorrow in the next lecture. But I can give you a kind of a bit of a preview right now, which is that what I'm sort of building to, what I was coming to next. I've just told you kind of what this dark matter looks like. The next step is, how does it talk to us? So as I sort of preview for tomorrow's lecture, one of the ways it can talk to us is by messing with the electron mass, for example, which will affect atomic energy levels. And then now you see, imagine your atom is bathed in this background wiggling scalar field that I showed this little movie animation of. Your atom will see if you like, if you're measuring the fundamental constants of nature, they'll appear to be changing in time because you're bathed in this dark matter field. And that will actually, for example, wiggle this atomic energy splitting. So you can turn the atomic clock around. I use it as a really good measure of time, but instead, if I compare two clocks, like I do in the gravity wave detector, I can use it as a really good measure of delta E. And that's what we do with the gravity wave detector, with the atomic gravity detector. So that's a bit of a sneak peek of what I'm going to say tomorrow, but I haven't really told you that yet. But great question. Yeah, is that clear? Did that answer it sort of enough, or?
Yeah, I think so, and I guess it'll be tomorrow too.
Yeah, great. No, that's a great question. Exactly.
Also, with the light travel time, I guess for gravity, it would be warping both maybe the light and the space between the atoms, or between the mirrors. And so I thought that there was two arms of LIGO, so you would be measuring, twice the light travel time instead of one single path. How do you do that when you?
Yeah, that's a great question, actually. And so this is actually, when I teach general relativity, this is a classic, great question that comes up. And in fact, I found many, senior physicists are still confused about this question. I've had many, many of my colleagues ask me about this, if they don't think about general relativity or gravitational waves a lot. The way it works. So you all may have, if you've seen general relativity, you may have seen this described in sort of two different ways. Let's say I have my two masses here, right? My two mirrors or something of LIGO, and I'm measuring how long it takes light to bounce back and forth between them, right? And exactly one very confusing way that we talk about it is we'll say, oh, the gravitational wave stretches and squeezes space, so that looks like it's making the laser take longer. Or, and I did this too, I was guilty of this too, or also it's an acceleration of the mass, right? And the mass moves, and that's what makes it take longer. And then you can say, well, wait, which is it? Or if it's both, do you actually have a signal? There's actually famously, I think even Einstein for a while thought gravitational waves were not real. They were gauge artifacts. There's famously been confusion about that in the literature. However, well, there's a longer story here, but the simplest way to say it is there's actually two different gauges in general relativity, which means two different, if you're familiar with general relativity, if not, my apologies, but if you're familiar with it, there's two different coordinate systems you can work in. And in one of them, the masses move with respect to those coordinates. And in the other one, the masses are fixed with respect to those coordinates, but the laser time is changed, okay? So the two different coordinates appear to switch where the effect comes in. Is it on the propagation of the laser, or is it the motion of the masses? And actually, the fact that it's coordinate dependent, it's like gauge dependence in E&M, it immediately tells you actually the question is not physical. The only thing that's physical in general relativity at the end of the day is an observable. Just like in quantum mechanics, really, you have to make a final observable. And that's how you avoid this sort of otherwise extremely sort of complicated confusions of where is the signal arising from. So when you make the final observable, there is of course just one, you can calculate, and this you sort of really have to calculate to be sure it's there. Like I said, in fact, in the beginning when there were people exploring general relativity, it wasn't obvious. But if you do a full, make a gauge independent observable, something that's coordinate independent at the end of the day, so it doesn't depend on which frame you're in, right? You will see that this thing measures some phase shift. And whether you ascribe it to motion of the mass or different propagation of light depends on which coordinate system you did the calculation in. But either way, there is only one answer, and it's the same answer. So in fact, a single arm of LIGO absolutely has the signal. You don't need two arms. Was that clear? That's a great question, by the way, and a point of confusion among even many senior researchers.
Yeah, that makes sense. So in theory, you could have like a 3-atom system, but it's still precise with 2 atoms.
Yeah, absolutely. That's right. And you're absolutely right, though. There are actually schemes, in fact, there are, I don't know if I can't get to my slide right now, but there are absolutely schemes where you'd want to arrange your atom interferometers maybe here, here, and here around a triangle, for example, with satellites, and make these links between them, sort of like Lisa-like, like a triangle, for example. That can have advantages. So absolutely you can do it. Just the cool thing with atoms is that you don't have to. In fact, I should say, as a little story, we were motivated to come up with this scheme of this hybrid clock accelerometer, which requires only a single baseline. We were motivated to do it because actually our first ideas required a configuration like this. In space, they required it, not on the Earth. I haven't told you why, but they required it, and we were working with a lot of people at NASA, Goddard. And they know how to fly satellites, and they kept telling us, boy, we're quite afraid of formation flying like this. You have to control the angles very, when it's 3 things, they form a plane instead of just a line. There's that many more angles to control, and it's very worrying to us. And they kept saying, can't you just do it with 2 satellites? That'd be a lot easier. And we kept saying no, until we finally came up with this new idea. And then we realized, yes, you can. And we think that's potentially a major benefit for this 2-atom approach, this 2-atom interferometer approach. Perhaps reduces some risk and some cost, especially for a satellite mission. Yeah, great question. So is that clear? Is that clear? And any other questions?
Yeah, that is, and it also kind of brings up because you're talking about like the costs of complexity.
Mm-hmm.
Earlier on, you're talking about like a theoretical optical setup with the beam splitters.
Mm-hmm.
At some point, is complexity a downfall? So if you were to send in a single atom into all these beam splitters, like at some point, it would get lost.
Very good. Yeah, that's a great. Mm-hmm. Mm-hmm. Yeah, that's a great point. Absolutely. And that is, I didn't say it, but exactly, you're right. Let me actually go. I think you're referring to like this picture here, for example. Absolutely. That's actually our limit, or at least one of the absolutely critical limits, which is when you lose the atom. The transfer efficiency to move the atom through all these different states is not perfect. They've gotten it really good. In fact, since the fact that they've got 100 pulses actually means they got it better than 1% loss of the atoms, better than 99% fidelity transfer. So you can put the atoms through 100 pulses and only lose at most sort of half of them, which is half is okay. We don't want to lose 90% of them, right? So they're able to do it a single pulse. They're able to transfer over 99% of the atoms, which is great. But you can see if we want to get to 1,000, we're going to need to do even better. And you need to limit spontaneous emission losses and lots of other things. So there's a lot of complicated atom optics, which I most certainly did not go into. But the practitioners of this art have to be, well versed in. And it's really beautiful and amazing that they can do it. As I say, I'm not the experimentalist, so I just really sort of watch and I'm impressed. But absolutely, that's one of the key points for sure. Was that the question you were asking?
Yeah, that answers it.
Perfect. Yeah, great. Yeah, great question. Good. Those are all great questions. Any other questions? We have a few more minutes if people want. I know you've all already been on a long time. Okay. All right then. So it sounds like no more questions. I am happy to stick around if anyone wants to stick around, but otherwise, thank you all, and I will see you tomorrow.